and I'm happy to see many people already in the audience. So one of the features of the IUCAA Colloquium is that we feature IUCAA faculty and their research from time to time. And always the youngest person to join the faculty, the most recent person to join the faculty is nabbed immediately when they arrive. And today we've done that. So with Muzahid joined us a few months ago. And actually, one of the reasons we have asked him to give the talk is that I have not seen him without a mask since he arrived. So now I can see his full face, which is great. And Sowgat is going to talk about something really, really fashionable. Sowgat was, of course, did his PhD here in IUCAA 2013. He came to us from Vishwaharati. And after that, he'd gone off to do several postdocs, Penn State, then Leiden. Then he was a Humboldt Fellow at the Leibniz Institute in Potsdam, where he got kind of stuck over the pandemic period. He was supposed to come to us before that, but then and then he took an opportune moment to make this transition from Germany to Pune. Welcome, Sowgat, and this is a very, very fashionable topic right now, and we are looking forward to how you use Muse in all these amazing surveys. Over to you.
Thank you so much. And thank you everyone for joining. So today I'm going to talk about two surveys that we are conducting with Muse. And as you can see the logo here, it's Multi Unit Spectroscopic Explorer built by 7 European institutes. And their logos are here. So I worked in 2 of them. Initially, I joined as through NOVA, which is like Netherlands participation, and afterwards I was at AIP. So I've been working with this Muse consortium for over 4 years or so. So today I'll be talking about how we can use Muse to sort of conduct surveys on the circumgalactic medium. And let's see what is circumgalactic medium. Okay, is it moving now, the screen?
Yes, Sowgat, yes.
Yeah, okay. Yep. So the circumgalactic medium, there is no strict definition in the literature, but it's generally considered as the reservoir of diffuse gas and metals surrounding galaxies. And the gas in the circumgalactic medium is likely to be bound to the host halo, but not necessarily. And it can extend out to the virial radii and even beyond that. So if you take the example of our own Milky Way, so the stellar mass is like 10.7 solar mass, and the halo mass is 10 to 12.3 or something like that. And then, which means the virial radii would be like 280 kiloparsecs. Whereas I showed this cartoon from a recent review on circumgalactic medium by Tomlinson et al. So this is the size of the disk. Like if you imagine that's the Milky Way. So this is the scale over which things will be luminous. But galaxy doesn't end here, right? There are lots of stars around them, and it's actually properly scaled. This is the 300 kiloparsecs length scale. And we know for sure that there are LMC, SMC, and Magellanic streams, lots and other low mass dwarf galaxies surrounding Milky Way. So it's not the luminous part which is important, because there are lots of gas. And in terms of volume, if you just see the how much volume there in the CGM compared to the disk, it's like 3 orders of magnitude, like 10 to 3 times the disk volume. So it's a huge volume filled with diffuse gas that is too diffuse to sort of emit any prominent emission. So it's difficult to probe the medium. So now that I'm not giving a job talk anymore, I can tell you what I really feel about this whole system, how I look at it. So this diffuse gas far away from galaxies are like a vineyard, okay? So it's nice, beautiful, but otherwise boring, unless you harvest the grapes to a winery and make a fine bottle of wine, right? And that's the star formation inside a galaxy. And that's where party starts. And when party starts, like that's how it happens, like the burst of coherent star formation or the supernovae can drive materials from the disk to the circumgalactic medium. And by the time we observed using quasar absorption line spectroscopy, which I'll show you, circumgalactic medium would look like something like this, okay? So it's a messy college student apartment after a party. It's very complex. So there are lots of like kinematic structure, phase structure, and it's dynamically like really dynamic medium. So that's the mess we are actually talking about. Jokes apart, so why do we really care about circumgalactic medium? So over the last decades or so, people have recognized that galaxies not only dark matter, stars, and ISM, but the circumgalactic medium is an important part of galaxy's ecosystem. And it actually, I'll show that there are three main sort of channels or three main questions one can address by studying the circumgalactic medium. And one of the major questions in this sort of study is how do galaxies interact with their surroundings? Meaning how do like gas accretion happens and gas recycling happens, and also how do galaxies drive outflows from the disk to the intergalactic CGM or even to the intergalactic medium. And circumgalactic medium can account, the baryons that are there in the circumgalactic medium can account for the halo missing baryon problems and also the missing metals. And finally, the circumgalactic medium observables, which are like equivalent with column density or covering fraction profiles, can constrain galaxy evolution models. I'll slowly explain like in next few slides what do I mean by all these. So let's start with gas flows. So what is shown here in the x-axis is the stellar mass of galaxies, and y-axis is the gas depletion timescale, so which is defined by gas mass that is available in the ISM divided by the rate at which it is forming stars. And for Milky Way type galaxies like L-star galaxies sitting over here, the depletion time scale is only a few giga-year. So unless there is a fresh supply of gas from the intergalactic medium, one cannot sustain the star formation for very long. And that it's not very surprising, but it's a nice way to show that galaxies cannot grow in isolation, right? Their gas has to come from the intergalactic medium to feed it. And next, in a more theoretical perspective, so that's the stellar mass function constructed out of HDSS. This figure is taken from Mach et al. Though the reference is a bit older, but the context is still relevant. So here you can see the observed stellar mass function of low-risk galaxies, and that's the prediction from the Millennium simulation. And you can see that the observations and theory actually disagrees a lot, both at low mass and at high mass ends. And it has been, at the low mass ends, it has been attributed to supernovae feedback, and at high mass ends, and it has been attributed to AGN feedback. So the energy or momentum that you inject to the ISM or in the CGM is actually prohibits further gas accretion, and it also heats up the gas so that you don't form stars very efficiently. And circumgalactic medium in this context serves as the reservoir of cool gas that fuels galaxy growth, and also the repository of metal disk gas that has been expelled to the by the galactic winds. So, and therefore the mapping the gas and metals in the circumgalactic medium and determining their physical and chemical conditions are very crucial in order to understand the galaxy evolution story fully. Next. So what I showed here is actually a plot from Magog et al., where x-axis is the circular velocities of a sample of local galaxies, and y-axis is the baryonic mass. And by baryonic mass, I mean the mass in gas or dust and stars. It's a very challenging experiment you cannot do if the galaxies are far away. So it's a handful of galaxies. They can actually have a good constraint on gas mass, dust mass, and stellar mass, and which should be ideally should be equal to the cosmic baryon fraction times the halo mass of those galaxies, and that's this line. So if those halos retain the cosmic baryon fraction, then all these points would be lying on top of this line. But the fact that the galaxies actually departure from this line, it means that they don't retain the cosmic baryon fraction, and this effect is more pronounced at low mass halos, owing to their shallower potential wells. And this is what is known as halo missing baryon problems. So you don't find all the baryons that you expect to detect in the halo. And the surveys, initial surveys of on the circumgalactic medium, for example, the Gauss halos team did a very nice job on this aspect, and they showed that the cool gas that are there in the circumgalactic medium can account for a significant fraction of the baryons that are missing from the halos. And basically the gas mass and metal mass is comparable to the gas mass and metal mass in the galaxies themselves, and that was one of the big results back then in 2011, when I was here as a PhD student. So, and finally, this plot, I'm taking it from Liang et al. And what is shown here in the x-axis is the distance from a galaxy center, and y-axis is the covering fraction of, on the left panel, it's magnesium 2. It's an ion that we detect in quasar spectra and from the halo of galaxies, and oxygen 6 and carbon 4. So what is covering fraction in the y-axis? It's basically in what fraction of the time you hit a magnesium 2 column density of here 10 to 13 when you shoot line of sights along a galaxy halo, towards a galaxy halo. So that's y-axis. And here the blue band is the observation from the literature. And the different curves are simulation prediction. That's what they did in this paper. Like they compare their simulation to observation, and their fiducial model is represented by this black line, right? It can reproduce a realistic Milky Way type galaxies with all those properties, right? For example, stellar mass, bulge to disk ratio, rotation curve, etc. And you can see that black line is actually failing to reproduce the observed covering fraction. And these covering fraction measurements are done in the circumgalactic medium, right? Miserably for both low ions, magnesium 2, and for high ions. Then they tweaked their model. So they artificially enhanced the supernovae feedback by 5 times, and also which is actually shown by the red curve, and also included cosmic ray winds driven by cosmic rays by some factor, so that they don't reproduce the galaxy properties very well. But now you see that those models, which are not reproducing the galaxy properties well, are actually doing better in reproducing the circumgalactic medium observations, the covering fractions, for example. So that's the sort of thing I wanted to sort of address here. And just to quote their paper, they say the simulation that produces a realistic lead type galaxy fails to reproduce existing observations of the CGM. And in contrast, simulation that does not produce a realistic galaxy has the predicted circumgalactic medium in better agreement with observations. And it's not only them, there is a series of paper, it's actually emphasizing these issues. And it's not only that they are not able to reproduce the covering fraction, it also happens when they talk about equivalent width profile, for example, or column density profile in the halo. So circumgalactic medium observables provide very strong complementary constraint, and any galaxy evolution model must reproduce the CGM observables self-consistently in order to be called successful. And people realize that this is a really interesting sort of challenge, and now there is a trend to sort of put more resolution to resolve the circumgalactic medium better, because earlier simulators used to use most of the resolution to resolve the galaxy disk, but now they are doing the reverse experiment. For example, now there are simulations that are available with kiloparsec or even sub-kiloparsec scale resolution to better understand the circumgalactic medium. I'm not going into detail of those simulations. Of course, that's beyond my expertise, but it actually tells you that a circumgalactic medium received a significant attention from the astronomical community. And if you are still not convinced, I did a little data mining using ADS, and what is shown here in the x-axis is year since 2000. So the 0 meaning the year 2000, and 2020 is last year, 2020. And y-axis is the number of papers in ADS with the word CGM either in the title of the paper or in the abstract. And you can see what is happening here. So the field circles are refereed paper, and the open circles are non-refereed paper. And that's the timeline when the HST course came online, and that's 2014 when VLT UBase came online. So clearly you can see after HST course came online, it's actually a whopping number of papers. And you see it varies as X cube if you do little fitting to this data. And in 1 year, in the last year, I think, yeah, there are almost 200 papers in the archive, or even published. So that's not a joke. So it's really interesting to see how this field is growing with time. So moving on, circumgalactic medium is diffuse. As I mentioned briefly in one of my initial slides, the density of the circumgalactic medium is 10 to minus 3 particles per cc, and therefore it's very challenging to detect in emission, though it's not impossible. For example, Sebastiano Cantalupo et al., they have detected extended Lyman alpha emission from luminous quasar at a high redshift. I think that's their so-called slug nebula, which is at redshift 2 or 2.3 or something. And afterwards, they also did a survey using Muse, and they find that the rate at almost 100% of the quasars they studied, they also extended Lyman alpha emission. And more recently, Lutz Wizarski and his team, again in the Muse collaboration, they also published the existence of Lyman alpha halos. Like even normal galaxies at redshift 3 that are detected via Lyman alpha emissions, which is extended out to 20 or 30 kiloparsecs. So it's not impossible, but it's challenging. And so far, it's circumgalactic medium signature in emission have been detected in only with Lyman alpha, since it's a strong transition. But Lyman alpha alone isn't sufficient to determine the physical and chemical conditions or kinematics of the emitting gas in the circumgalactic medium. And as you all know, the emission measure depends on density squared, whereas optical depth for absorption depends on density. So absorption line spectroscopy is the most sensitive probe to do circumgalactic medium studies. And this cartoon actually describes what do I mean by that. So usually in today's talk, I'll be using this absorption line spectroscopy technique to probe the circumgalactic medium. So what happens, you look at bright background quasar, which is far away from us, and then a text spectrum of that quasar. And the sight line of this quasar happens to sort of pierce a foreground galaxy. at some impact parameters. The projected distance between the background quasar and foreground galaxy, we call it impact parameter. And I'll be using that term over and over again. So it's better I explain it now. And depending on the sort of chemical composition, density, temperature, or radiation field that is there in the halo, it will produce absorption from different lines. And so we basically study these absorption lines to characterize the properties of the circumgalactic medium. So you can see that such study basically have such studies have two components. You need really good quality quasar spectra, along which you will probe the properties of the diffuse gas in absorption. And for that, we use VLT U-base data or HST cost data. And you also need a uniform galaxy survey around quasar fields so that you know which galaxy is causing absorption in the spectra, in your quasar spectrum. And the absorption signature and the galaxy, how do we connect absorption signature to a galaxy? It's a purely velocity connection. So once you know the redshift of the galaxy, you know, for example, let's say the redshift is at, the galaxy is at redshift 1, and the rest frame wavelength of Lyman alpha is 1215 angstrom. So once you know the redshift, you know where to look at in the spectrum, which wavelength to look at for their absorption signature. It's 1 plus z times the rest frame wavelength, as simple as that. But there are limitations with these studies because it probes gas only along a pencil beam sight line. And number of sight lines probing a galaxy, in almost all cases, it will be just one. And if you are very lucky, then there'll be like more, maybe two, but they are very, very rare. So in order to do a detailed circumgalactic medium studies, you need to have a large enough sample. And to do that, we are using Muse, okay? So Muse is a second generation instrument installed in VLT UT4. It's here. I don't know if you can see my cursor. So that's UT4 where it's installed. And that's the instrument. And it's me completely baffled by the sheer complexity of the instrument when I last visited in 2017. So Muse is an integral field spectrograph. It has 24 IFUs with field of view 1 by 1 arc minute in the wide field mode, and has spatial sampling of 0.2 cross 0.2 arc seconds in the wide field mode. That means it contains, each Muse field contains 90,000 spectra, and that's the beauty of Muse, okay? So at each pixel, you will get a spectrum, right? Or you can think of a different way, that at each wavelength layer, you will have an image. So that's really fantastic. The spectral coverage of Muse is ranging from 4,750 to 9,350 with a resolution of 3,000, which is like 100 kilometers per second, which will be about at 7,000 angstrom or so. So this Muse GTO team got 255 nines. And it has the team, Muse Consortium, has a very wide science interest from globular clusters to clusters of galaxies. And now I'll tell you why the instrument like Muse is best for circumgalactic medium studies. First of all, it's extremely time efficient, and it requires no prior imaging or prior imaging, in the sense all you need to know is that there is a bright quasar somewhere, and you just need to focus your telescope in that direction, provided that you also have a good quality spectra of that quasar. And since we don't require a sort of prior imaging, it allows you to blind detection. And you can also detect very low mass galaxies that are not very prominent in the continuum emission. But when you go to the right frequencies, you will see emission lines, right? And since there is no slit or fiber involved, So there is no sort of slit loss or fiber collision, which allow you to sort of measure fluxes very accurately, and that means you can also calculate star formation rate or metallicity of galaxies from the emission line fluxes very accurately. And what do I mean by extremely time efficient? I'm showing you by an example. So this is the field we observed with keck. So keck is a 10-meter telescope, and we use the ESI, which is single slit instrument. It took us a full night on 10-meter class telescope to get a redshift of the brightest galaxies in this field, nearly 7 of them. Okay, and then and here is a quasar. In this quasar, the cos spectra of this quasar shows a very interesting oxygen-6 absorption. You can show over here. It's spread over several hundred kiloparsecs. And at that redshift, we found this very massive galaxy over here, which is like 163 kiloparsecs. And we also did ionization modeling of this gas that is detected in absorption. And we found that the metallicity of this high ionization gas traced by oxygen is solar or even supersolar. So we thought that the outflow from this galaxy is actually causing this absorption. But here you can see this low ionization line, magnesium 2, which showed 10 times lower metallicity, okay, when we did the modeling. So we couldn't understand what is the origin of this low ionization gas that is detected closely at similar velocities. And when my collaborators from Swinburne, they were at Keck using KCWI, which is another sort of integral field spectrograph installed in Keck. So during twilights, they observed this field just for fun for 15 minutes, okay? And they observed this galaxy over here. You can see in magenta ring. So now this galaxy shows O2 emission, which is shown here in the channel map, with redshift matching with this absorption. So Hasti Nategi, who is an Iranian graduate student working at Swinburne, she published a paper recently showing that how this galaxy can help us understand this low metallicity cloud over here. So anyway, so IFU is really fantastic, and we need like deep observation, IFU observations in order to sort of get a good grasp on the circumgalactic medium studies. So now I'll be talking about MUSEQuBEs. And it stands for Muse Quasar Field Blind Emitter Survey. And the PI of this program is Jopsche, who is at Leiden, Netherlands. And in this survey, we have 24 quasar fields observed with Muse, using 120 hours of GT observation. And why blind? Blind because when we chose those fields, we didn't bother about whether those galaxies, whether those quasars have any absorption in their spectrum. So we selected those fields because good quality quasar spectra were available, and we didn't care about which absorption is seen in those spectra. Unlike some of the other Muse surveys, such as MAG survey by Michele Fumagalli from Durham, now at Milano, they are also conducting a large survey using Muse, but their sample is H1 selected. So they are trying to understand what is the galaxy environment of strong H1 absorbers like DLAs or sub-DLAs and so on. And also I'll be talking briefly about a megaflow survey, which is again, the sample is selected based on presence of magnesium-2 absorption in the quasar spectrum. And secondly, when we made these catalogs in these fields, galaxy catalogs, we did it blindly without sort of any prior knowledge about the CGM absorption in the quasar spectrum. And MUSEQuBEs is actually a dual program. It has low redshift part and high redshift part. In low redshift, we have, meaning redshift less than 1, we have a sample of 350 star-forming galaxies, and high redshift, we have 100 Lyman alpha emitters. In today's talk, I'll be mostly focusing on high redshift part since I'm leading the program. So in high redshift MUSEQuBEs, we have 8 Muse fields, as you can see here. And we used about 50 hours of Muse GT observation and targeted emission line through which we detect galaxies is Lyman alpha, and that's why they're called Lyman alpha emitters, because those galaxies are detected by Lyman alpha emission. And you can see that at the center of each field, there is a bright quasar, and for which we have U-based data, very high quality data, using about 120 hours of VLT observation. And those data have like resolution of 45,000 and signal to noise ratio between 70 to 100 per parsec, per pixel, not parsec. Yeah. And targeted absorption lines is H1, carbon 4, and silicon 4, and so on. And the redshift of the quasars in our sample ranging between 3.7 to 3.9, which allow us to sort of restrict our Lyman alpha emitter sample between redshift 2.9 and 3.8. 2.9 comes from the passband of Muse, because you cannot detect after, since there is a cutoff at wavelength 4,700 angstrom or so. And high redshift cutoff is coming because of the redshift of the quasar. You cannot go beyond redshift of the quasar if you want to do CGM study. And this is a very sort of optimal range to do this kind of study, because I can see it's coming from just from the night sky spectrum. You can see the Lyman alpha emission through which we will detect those galaxies will be in this band. And this band is actually free from any strong skylines except for these two. And the carbon 4 absorption, CGM absorption of those Lyman alpha emitters will be falling in this redshift, which is also not too severely affected by skylines. But if you go even higher, you can see how this skyline will mess up with your observation. And also a second reason is that if you go to too high redshift, then the Lyman alpha 4S absorption will be too severe in towards the quasar spectrum, towards the quasar sightline, and you won't be able to sort of have a decent measurements on the column density of those CGM clouds. So I think that's why we chose this particular redshift range and those quasars in our sample. So that's basically it describes the survey design. So it's here the Muse field of view center, there is a quasar, and there are two locations where we detected a Lyman alpha emitter. You can see the narrowband image here, which is at 170 kiloparsecs roughly. And once you extract the 1D spectrum, you can calculate the redshift. And as I explained, once you know the redshift, you know where to look at the absorption feature in the quasar spectrum. So that's the way it works. And you can see this Lyman alpha emitter is clearly showing carbon 4, strong carbon 4 and also strong H1 absorption. And the same thing for the Lyman alpha emitters detected here. And this, those who are experts, particularly for those, it actually shows the quality and richness of the quasar spectrum. So that's one of the sort of galaxies, Lyman alpha emitters in our sample. And those who are not aware of these plots, so zero velocity is the redshift of the Lyman alpha emitters. And the basically the absorption you see both blue and red is actually the gas kinematics projected along the line of sight. You can see we detect Lyman alpha, beta, gamma, delta, and so on. So it's a whole Lyman series lines, and also metal lines like C3, although it's blended but in the Lyman alpha forest, silicon 3, silicon 4, carbon 4, and so on. So it's a really rich data set to work with. So we have 96 Lyman alpha emitters detected in these 8 fields, with redshift less than the redshift of the quasar. And here's the impact parameter versus redshift plot, just to show the sample color coded by Lyman alpha line flux, Lyman alpha line luminosity. The median redshift of our sample is about 3.3, and median impact parameter is 160 kiloparsecs. So median properties, Lyman alpha flux is 10 to minus 17 arcs per centimeters per second. Lyman alpha luminosity is 10 to 42 arcs per second. And about half of them are also detected in UV continuum with a median luminosity of 10 to 42.7 arcs per second. And from that, we calculated star formation rate using the prescription by Kennecke. The median star formation rate turns out to be 1.3 solar mass per year. And if you assume that those Lyman alpha emitters fall in the star forming main sequence, then you can also sort of guesstimate what should be the stellar mass, and which turns out to be about 10 to 9 solar mass or so, slightly lower than that. And if you again assume the abundance matching relation, we use Moster, then the halo mass turns out to be 10 to 11 solar mass. And then you can always calculate what should be the R200 kind of for those structure, which is like few tenths of kiloparsecs. And Lyman alpha line equivalent width is 48 angstroms. And so that's the first results from our survey. So what we did, we used the redshifts of the Lyman alpha emitters and go to the quasar spectrum and stack them, right? And so that's what the absorption we see towards the quasar spectrum, the composite quasar spectrum. So that's the median stack on the left-hand side, and that's the mean stack on the right-hand side. And you can see both H1, Lyman alpha, and carbon-4 absorption is clearly detected, but they are blue shifted by 170 kilometers per second or so. Now, you see, since the Lyman alpha emitters are randomly oriented with respect to the background quasar, and we are actually probing the gas along the transverse direction, so there shouldn't be any preferred line of sight velocities. And the offset, the fact that it is not centered around zero, is coming from Lyman alpha resonance scattering. Because it is known that if you calculate your redshift from Lyman alpha emission, it doesn't give you the true systemic redshift. It's because of the large absorption cross-section of Lyman alpha line. It's basically given by this equation. And so Lyman alpha photons are really highly susceptible to neutral gas. And this plot I have taken from Berham et al. And Berham's paper. So it shows how intrinsic Lyman alpha emission would look like if there is a sort of column of neutral gas. So their model is basically mimicking a central starburst and then followed by ionized gas. It's just mimicking the H2 region and surrounded by a shell of neutral gas. Okay, and so basically you have the source of photon in the central starburst, and you're looking outside what is the emergent spectrum of Lyman alpha emission. And you can see as the NH1 increases, your line is shifted towards the red, like in positive velocities. And the cell is expanding, in this particular case, expanding with a velocity of 50 kilometers per second, which actually further suppresses the blue peak. So when in observation, you have a limited signal to noise ratio, you will always miss this part, the blue bump or blue peak of the Lyman alpha emission. So when you determine the redshift of Lyman alpha emitters, you will do only from the red peak, which is already sort of overestimated. So the fact that our lines are not centered around zero is coming from this factor, basically. It's because of the resonance scattering of Lyman alpha photons. So two other things to note here is that the velocity offset, how much it is offset from the 0 kilometers per second, should depend on the star formation rate, provided the expansion velocity is actually driven by star formation. And also, you can see as the line go from the line center to a higher velocity, the full width half max of the line is also increasing. And it's also inversely proportional to the equivalent width. And when we divided our sample into different bins of equivalent widths, star formation rate, and full width half max of Lyman alpha emission, we did find exact same trend. For example, it's shown here. You see, with equivalent width, we see the inverse trend. So for higher equivalent width samples, higher equivalent width bin, we find the velocity offset to be low. And the opposite for star formation rate, we see a strong like correlation between star formation rate and the velocity offset. And you can see also a full width half max. When full width half max for the low FWHM bin is lower compared to high FWHM bin. And these are all consistent with those simple cell model predictions. Moving on. So here, it's again taken from the same paper. In the x-axis is the full width half max of Lyman alpha emission lines, and y-axis is the velocity offset measured from systemic velocities for the individual Lyman alpha emitters, for which we know the systemic redshift from optical nebula lines. And these points are taken from Berham et al., which is like 2018. And they they suggested that there is a correlation between velocity offset and full width half max. And that's the shaded region is actually showing their scatter in their relation. And the blue points here is our circumgalactic medium measurements in the same plot. You can see that the same trend we can also get from circumgalactic medium observation, and that's quite remarkable. They got this trend from studying the ISM, gas in the ISM directly, whereas our study relies on the circumgalactic medium property, and yet we reached to the same conclusion in terms of the positive correlation between velocity offset and full width half max. And also we did the same thing for velocity offset and star formation rate. So these blue points are our own points. And this point is from Oliveira Rakic in 2011. So they did similar experiment, but for more massive galaxies at redshift 2.3. They studied the Lyman break galaxies using Keck baryonic structure survey, KBSS survey. And it seems like the velocity offset is increasing with star formation rate. And then we also looked at the literature from, for example, Trainer et al. Published for some of the Lyman alpha emitters, both the star formation rate and velocity offset, also the Shibuya et al. Points here. So except for a few points over here, it seems like there is a trend between velocity offset and star formation rate. So we did sort of, I don't know whether we call it a fit, since we don't have very many data points. But apparently this line can be explained as velocity offset is proportional to star formation rate to the power 1/6. And again, if you assume that they are actually probing star forming main sequence, then it will be like stellar mass to the power 1/6, which is like halo mass to the power 1/3, and that's is proportional to the circular velocity of the halo. And if you look at the momentum-driven winds model by Murray or Heckman et al., their wind velocity is proportional to the circular velocity of the halo. So it's actually all coming consistently. And so we said all this in the paper, and we also sort of emphasize that such empirical relations between velocity offsets and full width half max, or velocity offset and star formation rate, can be used to calibrate, at least on a statistical sense, Lyman alpha redshifts when you don't have like true systemic redshifts from optical nebula lines or any non-resonant lines, basically. Now, switching gear, I think now I'll show you a few plots that are in prep. So the experiment is very simple. Now what we did, we split our sample into different bins of star formation rate or environment or redshift and so on. And now here I'm showing you the dependence of CGM absorption, the stacked CGM absorption on star formation rate. So here we divided our sample into 3 bins, high redshift, which is, high SFR, low SFR, and those Lyman alpha emitters for which we couldn't place any, we couldn't measure the star formation rate properly. So we can only put limits. And you can see there is a strong sort of a trend between high SFR and low SFR bins. And it seems that the high SFR bins is showing a very strong H1 absorption compared to low SFR bin. But carbon 4, which is metal line, it doesn't show any strong trends with SFR, though the line is weak and noisy. And we think, but here the catch is that the trend that we see in H1 cannot be due to material entrained by star formation driven outflows. It's simply because if you assume those models, momentum driven outflow models, and the outflow velocity is proportional to circular velocity, then the outflow velocity from these structures will be like 120 kilometers per second. And the time scale over which the star formation rate, our star formation rates are calculated from UV continuum, and the associated time scale is like 100 million year. So if you multiply the outflow velocity and the time scale of the star formation rate, is only 12 kiloparsecs. And if you can remember my binary slide, so this tau SFR is the time, how long the party went on, right? So, and basically V outflow is that how drunk you were. So that's how you can explain. And so when you multiply this V outflow and tau SFR, it's only 12 kiloparsecs, whereas our median impact parameter is like 160 kiloparsecs. So therefore, we think that this trend, though we see strong H1 absorption, stronger H1 absorption for high SFR bin, it cannot be due to the entrained material from the outflow, unless the party went all night. Like the SFR has been high for a very, very long time, much more than like 100 million year, or the outflow velocity is really, really very high. Instead, we think that the high SFR is the consequence of the availability of cool gas in the circumgalactic medium. Since CGM actually controls the gas flow, the halos that are surrounded by more gas, like neutral gas, are like more sort of in a favorable condition to have higher star formation there. Moving on, so then we did this sort of study to see whether the environment is playing any role in determining CGM absorption. And we split our sample into group and isolated subsamples. And group is very like a simple definition. We try to see basically whether there is any like Lyman alpha emitters within the Muse field of view and within plus minus 500 kilometers per second or so. Okay, so that's the very simple-minded definition of group. It's basically, ideally, you should call non-isolated. But whatever the definition is, we see there is a strong trend. The Lyman alpha absorption and both carbon 4 and Lyman alpha absorption is way stronger when there are multiple galaxies or when there are multiple Lyman alpha emitters compared to the isolated ones. And this is consistent with what has been seen for low redshift magnesium 2 absorbers. For example, Bordeaux et al., they have seen the same trend. And they proposed a scenario where in the case of group galaxies, your sight line is probing multiple halos. And that's what you get higher equivalent widths for galaxies that are in group. But in a later paper by, I think, someone, they showed that the kinematics in that case, if it is just the superposition of multiple halos, it actually messes up with kinematics. In a recent paper by Fossati, they also says that stripping of gas from the halo to the intergroup medium can also enhance the cross section of your gas, which can actually cause higher absorption, like in case of group galaxies. But since our impact parameters are really large, we think that probably the group galaxies are surrounded by more like rich large-scale structure, which is causing this enhanced absorption in the case of group galaxies. But we don't know for sure. It's a work in preparation, and I'll be happy to know your viewpoints in these results. And finally, here I compare the equivalent weight profile. So how the Lyman alpha equivalent weight changes with impact parameter. And I compare different samples at different redshifts and different types of galaxies. I know this plot is busy, but let me explain. So this rate point, those are simple. So these are from this work, our Lyman alpha emitter sample. And these green and blue points and this horizon, not the power law line, this dotted line, is all are from the KBSS survey, which is the survey by Chuck Stadel, at different stages of their survey, basically. Stadel, this blue points is 2010, green points it's as 2014, although there is a slight difference in also in terms of the technique they used. Turner et al., the green points, they use background quasar, whereas Stadel, he used the background galaxies or the Lyman break galaxies themselves. But anyway, so the main point is that the rate points, the equivalent ways that we measure are comparable to Lyman break galaxies, which are at redshift 2.3 in the KBSS sample. And there are other data points in triangles. I'm showing in the cos halos and cos gas surveys, which is redshift 0.2. And also Prochaska 2011, which is like sub-L-star galaxies, dwarf galaxies, redshift 0.1. So you can see our measurements are actually comparable to those Lyman break galaxies and L-star galaxies, and higher, significantly higher compared to low redshift dwarf galaxies. On the right-hand panel is the same, but now I scale the x-axis just to take away the effect of mass. Since they are different surveys probing different types of galaxies, they will have different virial radii. So in x-axis here, it's the R by RVL, the impact parameter normalized to the virial radii. Now you can see at a given normalized impact parameter, the Lyman alpha emitters are it turns out to be they are more rich in neutral gas, H1 gas, which is really surprising and interesting. And you can see clearly also that it's also significantly higher compared to lower redshift 2 of galaxies. So I think now I'm in a position to summarize my high redshift MUSEQuBE survey. So we present the first ever statistically significant sample of Lyman alpha emitters for CGM studies. We have 96 LAs at redshift 3.3. And we showed that the stacked CGM absorption can be used to calibrate Lyman alpha redshift. We observed a velocity offset of about 170 kilometers per second. And the velocity offset is correlated with full width half max and anti-correlated with equivalent weight of Lyman alpha emission. And these are consistent with theoretical predictions of Lyman alpha resonance scattering. And velocity offset is also correlated with star formation rate, which we think that it's coming from the velocity offset is proportional to circular velocity, and which is again proportional to wind velocity. And gas and metals are widespread around Lyman alpha emitters and out to like 5 virial radii. And Lyman alpha absorption shows a strong environmental dependence and star formation rate dependence. And environments of Lyman alpha emitters are more rich in H1 gas compared to Lyman break galaxies at a given R by R 200. So yeah, I think I used all of my time. So I should stop here, but I have a few more slides. If you're interested, I can show you.
Thanks a lot, Sowgat. That was a talk which one has a lot to muse about. So, sorry. So, if any questions, please raise your Zoom hand and I will unmute you. I think people are used to the Zoom hand. Okay, let me then begin by asking. There are already two questions. Okay, let's give Dipanjan, please unmute yourself and ask your question.
Yes, I am at home, so I'm not sure whether my internet connection will work. So if you can you hear me?
Yes, we can hear you. We can hear you.
Okay, so I have two questions. One, a very more specific question. Can you go back to slide 23?
Oh, wow.
Okay.
Yeah, so I didn't really catch what is the strong correlation here in the H1. Are you talking about the width of the line?
That is also, and the equivalent weight, right? If you see, it's like 1, and in the other case, it's 1.6. So it's like factor of 1.6.
Okay,
and yeah.
Right. So I didn't really understand your final conclusion. So you have listed in the black some of the arguments which you say can produce probably large widths, but you don't subscribe to that. What you say is it's more high star formation due to gas around it. How does that correlate with the increase in width?
No, I'm actually trying to see the overall amount. It's not the width, but the equivalent weight. So equivalent weight is like more neutral gas surrounding them. And is it because you driven a lot of material in the CGM because of the star formation or not? But that's
right.
what I said, like you cannot do that because your flow won't move.
So this goes back to the fact that you need feedback. So I was confused by your last conclusion where you said that there's a lot of neutral H1 gas. So it could be, so there's this debate about accretion versus feedback, whether the gas in the CGM is being fed by fresh accretion streams. And one way to probe this is also through the metallicity, because if you have fresh accretion, then that will reduce the metallicity. And on the other hand, this will increase the metallicity. So I was a bit confused between these two things. So can you comment on that? What causes this extra gas?
Yeah, so metallicity is definitely a better indicator, and we will be doing that in the next project because it's a lot of work. Because now I'm just stacking it. We are doing stacking not because we don't detect individual absorption line, as I have already showed in one of the slides. We are doing because it's easy and you can do quickly. And so we'll do that at some point. But here what we see that on an average, when you stack them, the sample, the subsample that are showing higher star formation rate is showing higher like equivalent weight of Lyman alpha absorption. And so I'm not saying that there is no feedback. Of course, there will be outflows, but that will be affected in the immediate vicinity, let's say 50 kiloparsecs or so. But the median impact parameter that we probe in our sample is like 150 kiloparsecs. So it's really far. So that's all I'm trying to say. So what I'm trying to say, the way I try to understand is that it may be the large scale structure in which these Lyman alpha emitters are embedded in is actually causing this absorption, because we are so really far from the Lyman alpha emitters.
Okay. And do I have time for one more quick question?
Should we come back to you, Dipanjan? Or?
Yes, sure.
Yeah. Biman? Biman, can you unmute?
Hi. Yeah, can you? Yeah, hi. Sowgat, very informative talk. I was hoping that you would say something about the molecules.
So
I think it's very intriguing, right?
Yeah, so we actually did back in 2015 the molecular hydrogen studies without paying much attention to whether there are any galaxies around them. And people actually do like, I think we are the among the first people who show that you can use the cos spectra, the archival cos spectra, and there are sort of I think, if I'm not forgotten, the detection rate of H2 in sub-DLAs that we surveyed back in 2015 was almost like 60 or 80%. And in some cases, there were galaxies, the closest bright galaxies was like 50 kiloparsec away. So that was really puzzling for us. And we tried in a couple of times to sort of get Muse time to do a follow-up for those. But when you are not with the Muse consortium, getting Muse time is really, really hard. So our proposal never got accepted. So we couldn't do a detailed sort of galaxy study around them. But there is I think it's a decent sample of molecular hydrogen absorbers using COS. But
was it typical impact parameter?
Typical impact parameter, yeah. So I think it was, in most cases, it was like less than 30 kiloparsecs. But in two cases, the nearest bright galaxy for which we had redshift was like 50 or even 70 kiloparsecs. But now, in those cases, we were using what is there in the existing literature. We didn't do any survey, but I'm sure if we had if we get a Muse time for those fields, we'll certainly detect like more galaxies around, like closer to quasars. Unfortunately, this is beyond the sort of this.
Thanks, sir. I hope you get some time, and then this will be very interesting too. Yeah.
Yeah.
Thanks.
Thank you, Bhima. Narendranath.
Hi. So I had two questions, but okay. So can you go to slide 24 where you showed two groups and isolated? Yeah, this one.
Yeah.
So if you see the trend actually in the top panel, that carbon 4 line and the H1 line, the width of the lines are actually opposite trend, right? So in group sample, you see the carbon line is actually narrower as compared to the isolated sample. But in the H1, it is actually opposite. So it's kind of, if I say that, okay, if you have group of width are there, so I mean, how do you reconcile that?
Yeah, that's a very nice observation. But I think C4 being very weak, I won't put my money on the line with at the moment. So I think we can say anything definitive about that if we have a much larger sample size. It's really noisy, but equivalent with is, I think it's somewhat larger. Yeah, so to answer your question, I don't know whether I trust those weights very much. And let's see, are they consistent within 1 sigma? And they should be. Yeah.
Okay. So, I mean, I have a quick question. So this SFR versus this offset, okay, so that you say that you can calibrate the Lyman alpha emitters redshift, but doesn't it depend also the impact parameter? Because if you kind of believe the cell model as you go far and far away, so I'm kind of confused. This offset, so for different impact parameter, I would expect the offset would be different, as the simulation also showed. So,
in a different impact parameter, actually, that we did, and you see the impact parameter. It's not that different. Okay. So that's the two impact parameter bins, and they are pretty much consistent with each other. Yeah, so we didn't see any trend with impact parameter. Yeah.
Okay, so that is kind of confirming that it is purely CGM thing. I mean, not much SFR impact. I don't know. I mean,
no. So, okay, let's see. So, where is this plot? Yeah. So the. Okay, so what was your point here again?
Yeah, my point was, see, SFR, I mean, this is the SFR of the Lyman alpha emitter, right?
Right. That's
and the offset you are talking about, the stacked offset from the quasar line, right?
yes.
Yeah, so I would expect that if the impact parameters are higher, for example, you are far from the galaxy or quasar is at far distance, so then I mean, this offset is, if it is coming from the whatever the star formation activity is going on in SFR in the cell model, what you talked about. So if you go far and far impact parameter, the effect would be less and less.
Okay. So right, yeah.
Anand seems to have a comment in the chat box.
Okay, what is that?
He says shell radius is nothing to do with the impact parameter.
Yeah, that is also true. So because why? Because let me see. So I think there is a confusion. So so this SFR, we are actually calculating using Lyman alpha line, and velocity offset using circumgalactic medium. So it doesn't matter how far you are from the galaxy. Because it's the CGM gas which is causing the absorption, right? So it's not that we're probing the
yeah, okay. I get your point. Yes, so it is basically the property of the CGM, not much thing to do with the SFR. Okay, fine, yeah.
So Anand, did you have anything to add? I unmuted you.
Can you hear me? I just want to say the offset you are seeing is at the location of the galaxy itself, and if shell is producing the offset, it cannot be at 100 kPa, isn't it? So this is a model. I won't believe the shell. Basically, what it tells you is that radiative transport in the galaxy will shift the lines, broaden the lines, and blue part will be suppressed. So I think the point which is relevant for Sowgat's comment is that where do you stack them? This is the stacking, because to get a line profile, you have to stack it at the correct redshift, and Lyman alpha peak will not give the correct redshift. So I think this is all crude estimate. We should just take it like what he was saying, and that's why I will also not believe the width, because the width what you are getting is also depending upon delta Z you can assign. So if you say that star formation division, low star formation and high star formation, the offsets is also correlated. So your width, I will not believe the width FW, even if Sowgat says that signal to noise is good, because there is a systematic spread which comes from where is the emission rate.
Okay, great. Thanks, Anand.
Thanks.
Shaha, can you unmute?
Yes, thanks, Kanak.
Oh, this is Kanak. Okay, I was wondering who is Shaha. Yes, Kanak.
Sowgat, I think I wanted to know, now that you have Muse and this CGM studies, like sort of growing very much. So is there a scope for doing now kinematics in the CGM?
Yes. So I presume that what you mean by kinematics is like your line of sight kinematics that we see along the line of sight. Is that what you?
Yes.
Yeah. So that's what I don't. Okay, I don't know why it's going the other way around. So you can see now we are doing stacking because it's easy and simple. You can see this kinematic structure in this particular plot, right? If you see that carbon 4, at least there are 3 components, and also in silicon 4 there are few. So we have this data with us, but then someone needs to analyze them carefully. So yes, we will go into that direction once the paper in preparation is done.
In other words, basically, could it be possible to exactly pinpoint that gas is accreting?
Oh, that's a really challenging question.
Because that's the That you want to catch them, right?
Yeah. So I think the reasonable next step would be to sort of make bulldoze through the data and produce observables, and then try to sort of compare with like models, or even build simple analytical models to see whether you can explain the line kinematics, or the total absorption, or weights, or whatever with those models. I think that's the way we need to head on. But as of now, we didn't do any of those
Yes,
things.
yeah, I understand. I just wanted to know, like,
Yeah,
if someone
but
is doing
that's
it.
definitely is the logical, would be logical next step.
Yeah. Thank you.
Dipanjan, can you ask your other question if you... Dipanjan?
His internet is gone probably.
No, I'm here. I had to convert to unmute me. So I had a question regarding the nature of the host sources. So since this is a survey, what you are trying to really quantify is something regarding the host galaxy. First, my question is, what are the mass ranges of the host galaxies that you're looking at? If I remember correctly, you said something on 10.9 solar mass.
10.9, yeah, right.
So this is, you're really focusing on the lower side below the break.
Yes.
Any intention of your survey team to go to the high-end mass of part of the masses?
Right. So as you know, the more massive galaxies are rare, and therefore you need larger area to be surveyed. But that anyone can do. Like, you can choose the brightest galaxy, more massive galaxies, and do CGM absorption studies. But the challenge is to sort of probe the low mass galaxies. It also makes whole thing complicated, because now instead of one galaxy, there will be many galaxies, and you're completely puzzled, like what to do with those. So Muse is allowing us to do that for the first time, to go really deep and pushing the mass into really low mass limits. So 10 to 9 is like how much? It will be like SMC or LMC type structure. So
Yes.
I think that is more exciting compared to going to the bright, more massive galaxies. And that's really new. Like, these galaxies was really untouchable without IFUs.
Okay, thanks.
Anand, you had a question or a comment?
I have a question. Have you tried the inverse problem?
Yeah.
For example, you take strongest absorber in your spectrum and stack the data cube to see the diffuse emission, like the way people have done. I don't know whether you will have that many absorber to go. So
Yeah,
it's like doing Lyman alpha emission versus Lyman alpha absorption cross correlation.
right.
Because like you have up to some kiloparsec, right? How much you are going? 100 kiloparsec or 200 kiloparsec?
It's 300 kiloparsecs.
Yeah. So in the 300 kiloparsec range, can you do? See, this is like intensity mapping kind of, right? You take the Lyman alpha, and you can do the cross correlation of Lyman alpha with pixels.
Yeah.
Simply to ask, is there any faint galaxy? If there are correlations with faint galaxies,
right,
you should find something. I don't know how to do it. Maybe you should put rings around each absorbers and calculate mean light as a function of ring radius. I don't know.
So,
Maybe it's interesting to explore. Because if you have thousands of pixels, you may have a signal to noise improvement of several tens, I suppose.
Yeah. So I think I understand what you are saying. So you are saying that you take the redshift of the strongest absorber and stack the image, right? So that's what you are saying. Yeah, and you have told me to do that, but I couldn't do that.
So I didn't talk to him, by the way.
Yeah, he told me like 2-3 years back, but I didn't reach to that point. But if you're interested, Rajeshwari did a very cool stuff on that aspect, but at low rate.
If I told her, she would have done it.
Yeah.
Anand, you have no more control.
Okay.
Sorry.
Yes.
Yeah.
Okay, what was it? This thing? She did for MG2 or what?
Yeah, for MG2. For MG2 absorber and then O2 emission. And she did find some signal.
Oh, okay.
Yeah, that's really cool. Our last paper, actually.
Okay, good.
Kanak, do you still have a question? Oh, your hand is still up. Kana?
Okay, probably he forgot to put it up.
Okay. Oh, okay. Then I wanted to just ask you just
Sorry, Kandu, I think I forgot to lower my hand.
okay,
So,
okay, fine. Yeah, so you had this plot where you showed that things went up to 10 times the virial radius?
5 times.
Five
Yeah.
times.
So you see, these Lyman alpha emitters, they are really low mass structures. As Dipanjan was mentioning, it's 10 to 9. So virial radii is like 30 to 40 kiloparsecs.
Okay.
Yeah.
So it's not a big cluster or something. I was
Yeah.
completely zapped. Yeah.
Yeah. So if there are no other question, I'll just go to my last slide. Is that there are only...
Sowgat, there is just one more question in the chat box.
Okay.
By Manami Roy. Do you see any metals beyond virial radius?
Metals beyond virial radius, yes, because we do see stack carbon for absorption, and it's a clean detection beyond 3 sigma at least. So the answer is yes.
Okay, please go. You wanted to say something more.
Yeah, so that's my last slide. I don't know if people can see it. So I just to emphasize that only 6 people are actively working on all these projects, and like I couldn't talk about MEGAFLOW at all. And 2 of the major players working on low-Z MUSEQuBEs left astronomy. So we need more people. So if you're a first-year student and really excited about observational astronomy, so we have the best quality products to offer you. So please come and talk to me.
Yes.
Okay.
Yes, very good. Okay, great. Thank you very much, Sowgat, for this